corresponding hypothesized population parameter. So in general, we say it is a formal statement or assumption about a population parameter. So here whenever we are understanding about an hypothesis statement, we have to ensure that hypothesis testing requires null hypothesis which should be considered as true. That means there is no difference, or sometimes we say the statement is a status quo until it is proved false on the basis of the results which are observed from the sample data. So we have actually the two types of hypothesis. One is the null hypothesis and another one is the alternative hypothesis. So always the null hypothesis is expressed in the form of an mathematical statement which includes greater than or equals to, less than or equals to, making a claim regarding the specific value of the population parameters. So if I want to define null hypothesis, the null hypothesis which represents the default or no effect scenario, it assumes that there is no significant difference or relationship. When it comes to the alternative hypothesis, which states that a specific population parameter value which is not equal to the stated. So we say that it is actually the negation of the null hypothesis. That means on what basis we are taking up that statement is very important. That's why we say the alternative hypothesis which represents the research claim or the effect of interest, it is accepted if there is enough evidence to reject the null hypothesis. So generally we are testing the statement because the null hypothesis is considered true always. That's why we are stating that null hypothesis is a status quo statement. When it comes to the hypothesis testing, especially when if you want to consider the type of the test, how we are going to consider, because the nature of the test is very important. The nature of the test is very important because you have crafted you have stated the null hypothesis and alternative hypothesis. Nature of the test, when it comes to the nature of the test, we have two-tailed test is there, we have right-tailed test is there, we have left-tailed test is there. But how do we decide whether it is one-tailed or two-tailed? Because it always depends on the direction of the research hypothesis and the question which is being addressed, especially in the statistical test. So generally, how do we understand hypothesis? When it comes to the null hypothesis, we say that that there is no effect, or there is no difference, no relationship. So when we have the statement where there is no effect, where there is no difference, where there is no relationship, then we can understand that it is a null hypothesis. In the alternative hypothesis, always a statement that there is an effect, there is a difference, and there is a relationship. So here the alternative hypothesis which helps us to determine whether the test is one-tailed test or two-tailed test. One-tailed test or two-tailed, how we are coming to a conclusion based on the alternative hypothesis. We are determining whether it is a two-tailed test or one-tailed test. Because in the one-tailed test, always the alternative hypothesis which specifies a direction of the effect, whether the effect is greater or whether the effect is less, or whether the effect lies only at one particular side. That's why always the rejection region lies in one particular tail of the distribution. So generally, when to use this one-tailed test? Suppose in your hypothetical statement, if there is a specific directional statement, if it is a specific directional statement, then we consider that it is a one-tailed test. Sometimes we use, suppose if the test is to study or to test whether the parameter is greater than or less than a specified value, then we use a one-tailed test. When it comes to the two-tailed test, a test always, suppose if the alternative hypothesis is not at all specifying a direction, consider that it is a two-tailed test. So here the possibility will be there in both the directions. So the rejection region, that means we call that as a critical region. The critical region lies in both the tails, left tail as well as the right tail. That's why when we are basically we say, when your hypothetical statement which is a non-directional hypothesis, then you have to use a two-tailed test. Say for example, example for the two-tailed test, H naught, where mu population is equals to mu population naught. Alternative hypothesis, when mu population is not equal to mu naught, then we say that it is a two-tailed test. Suppose if mu population is greater than mu naught and mu population is less, alternative hypothesis where mu population is less than mu naught, then we say that it is a directional hypothesis, so it is a one-tailed test. And specifically, if you want to say, even in the one-tailed test also, if it is a left tail or right tail, always in the even how we are determining based on the alternative hypothesis. Say for example, x mean which is greater than or equal to mu population, then we say that it is a right tail test. It is a right tail test. That means null hypothesis. When it comes to the null hypothesis, what will be the null hypothesis for this? X mean will be less than mu population. So here, on what basis we are determining the type of the test or nature of the test is basically based on this hypothetical statements. Only one thing you have to keep in your mind: if it is a directional hypothetical statement, then consider that it is a one-tailed test, and if it is a non-directional, then it is a two-tailed test. So that's what here in this particular slide which is mentioned. So when it comes to even when we are observing this, especially significance test of in the hypothesis testing. How we are testing? We are testing for large samples. We are also testing for the small samples. Suppose when we are dealing with large samples, see here what we are going through on the screen. If you observe, test of significance of a single mean for large means. Single mean for large means. Large means means large samples means here, especially when n is greater than or equal to 30. If sample size is more than 30, then we apply the test of significance of a single mean we perform to determine whether the sample mean differs from the population mean or not. That's why we apply here the test statistic for a single mean in a large samples is given by the z-score formula, where where x mean is considered as a sample mean and mu is considered as a population mean, and standard deviation which is considered as population standard deviation, and where n will be the sample size. And how do we determine the critical value? Here also from the, especially from the z tab, we find the critical z values for a particular level of significance, and then we take the decision. If it is a two-tailed test, always critical values, say for example plus or minus 1.96. If it is a one-tailed test where alpha will be 0.05, that means this level of significance will be 5%, then the critical value will be plus 1 minus 645 minus 1.645. So here the positive value considered as a right tail, and the especially left tail considered as a negative tail. And how do we accept or reject, on what basis? Suppose if mode of z is greater than, if it is z calculated value is greater than the z critical value, then reject the null hypothesis. So vice versa. If z calculated value is less than z critical value, then we fail to reject the null hypothesis, and we say as there is no significant difference, so we accept the null hypothesis. H naught is accepted. So here there is a problem for understanding test of significance of a single mean, especially large samples when considered large samples. So here a packaging device is set to fill detergent powder packets with a mean weight of 5 kg with a standard deviation of 0.21 kg. The weight of packets can be assumed to be normally distributed. Now see here, when it comes to the problem, we have to state the hypothetical statement. So here what do we take from the problem statement? We can take that the mean weight has increased. Mean weight has increased. So actually here this particular hypothetical statement is a directional hypothetical statement, because what I am taking, the mean weight has increased. Increased is there is a direction. So it has increased. So null hypothesis will be considered as mu population which has increased. Increased means greater than 5. And alternative hypothesis, exact negation of the null hypothesis is the alternative hypothesis, so will be considered as mu less than 5. So look at the solution. If we look at the solution here, what we have taken the statement, by taking the null hypothesis, the mean weight has increased. So I am considering the null hypothesis increased. So when it is increased, it means a directional statement. It is a directional statement. So I am considering mu population has increased the 5k. And negation of this will be the alternative hypothesis. So based on the alternative hypothetical statement, I decide whether it is a left tail test or right tail test. So from the problem it is observed that the sample n is 100 and mean weight already given in the problem, so no need to calculate. So 5.03 kilograms, and standard deviation given alpha at the level of significance, 5%. So using the Z statistics. So always Z statistics is used where large samples is considered. When n is greater than or equal to 30, then definitely we use the Z statistics. So Z statistics, which is x mean minus mu by standard deviation by root n. So when we simplify by substituting all the values, we have Z calculated value as 1.428. So since as the Z calculated value is higher than, see 1.428 is higher than minus 1.645 left tail. So left tail means always the critical values will be in the negative. So as we have the positive calculated value, so when Z mod Z is greater than critical value, Z critical value, then reject the null hypothesis. So here in this case also, in this problem also, we are rejecting that particular statement, stating that the mean weight has not increased. The mean weight has not increased. So that is our test. That is our test, especially for a single mean when large samples are considered. And we are considering the same thing when we have two means. Suppose if you are having two means, because here what we are determining, whether the means of two independent samples are significantly different. We are considering that two independent large samples. So here what we have considered, sample as x1 as sample mean and x2 as a sample, another sample mean. So two independent sample means we have considered, and we are stating that significantly different, and this particular test is applicable only in both cases, both samples, sample x1 and sample x2, where the sample size should be more than 30. So here what kind of null hypothesis, that there is no significant difference. That's why here sample variances also we have to sample variance 1, sample variance 2, and sample size n1 and n2. So with the test statistics is calculated as x1 minus x2 square root of s1 square by n1 plus s2 square by n2. When we look at a particular problem, then we can understand. So we look at some problems. So the material is already shared with the students also. So you can go through and you can practice more problems to understand the concepts well. So here how we are crafting here the we are stating the null hypothesis. What is that? Two means are equal. The two population means what is the population mu population 1 and mu population 2 which are equivalent. Alternatively, we can state that mu 1 minus mu 2 is equals to 0, and always the process is same for almost all the statistical test, two-tailed test where it is not equal to and greater than, less than, which is considered as a left tail test, and on what basis? Based on the alternative hypothesis. Suppose now here there is an example. What is that? A firm believes that the tires produced by process A on an average last longer than tires produced by process B. So to test this belief, so there is a statement, belief statement. So that's why what we have taken here, the null hypothesis, that there is no significant difference in the average life of tires produced by the process A and B. Firm believes that tires produced by process A on an average last longer than tires produced by the process B. So there is no signal. So we are considering that as a null hypothesis. So we have taken population 1 is equals to population 2 and population not 1 is not equals to population 2. So based on the alternative hypothesis, we can clearly state that it is a two-tailed test. So x1, what is that x1? X1 we are considering the average lifetime and standard deviation he has already given in the problem. So standard deviation 1 and standard deviation 2, for both the process it is same, even the sample size also same. That's why n1 is equals to 50 and n2 is equals to 50. What is that? Only lifetime, average lifetime, because here this is the major part that where we are testing whether last longer than tires produced by the process A or B. So all the things are common. Only the average lifetime for process is A is 22,400 kilometers, whereas for process B 21,800. So here we are taking 5% significant level and using the test statistic Z. So as it is the case of two means, so we are taking two means, that is the average lifetime process A, process B. So x1 minus x2 square, standard deviation 1 and standard deviation 2 square, n1 plus n2. So by substituting the values and simplifying, we get 3. And Z calculated value, here Z calculated value is 3, which is more than the critical value Z alpha, that is equals to plus or minus 1.645 at the level of 5% significance. So we are rejecting the null hypothesis. So like that, here there is a test, but here if we observe vitamin C, no vitamin. So sample size. So sample size 35 given, and sample mean, that is x1 which is given as 5.8, and sample standard deviation, that is standard deviation 1, especially for vitamin C, given as 1.2. And by taking the level of significance, so we are calculating the test statistics as x1 minus x2 by square root of s1 square plus s2 square by n1 plus n2. So again, using the z calculated value and critical value, so as it is greater than, z calculated value is greater than the z critical value, hence null hypothesis is rejected. And this is another important test for single proportion, especially for the large samples, when you are taking the large samples. So here also, whether observed proportion is significantly different from a population proportion. So here we are applying this test again when n is greater than or equal to 30. So as it is a single proportion, test statistics which is calculated as small p minus uppercase P divided by square root of P into 1 minus P divided by n, where small p is considered as the sample proportion, that is P is equals to x by n. X will be successes in the sample, and uppercase P, which is considered as a population proportion, and n is considered as the sample size. So here there is a small problem for understanding the concept. So an auditor is claiming that 10% of customers' ledger accounts are carrying mistakes of posting and balancing. So a random sample of 600 was taken to test the accuracy of posting and balancing, and 45 mistakes were found. Are these sample results consistent with the claim of the auditor? So we are using a 5% level of significance. So here what is the claim? An auditor claims that 10% of customers' ledgers accounts are carrying mistakes of posting and balancing. So we are claiming that auditor's claim is valid. So what is the percentage here? How much percentage he is claiming? 10%. So single proportion small p is equals to 0.10, and alternatively which is not equal. So when it is not equal, so based on the alternative hypothesis, I can state that it is a two-tailed test. So calculating the when it comes to the calculation, so t statistics, small p, we got we have 0.075 minus uppercase p is 0.10 divided by square root of 0.101 minus, by simplifying this we got minus 2.049. So as z calculated value is greater than the z critical value, which is 1.96, hence null hypothesis is rejected. In the same way, the test of significance of difference between two sample proportions for large sample.